I will be speaking about DedupSearch, work I've done with Shilane, Sarai, Sheinvald, and Gala, Yadgar. It doesn't work. So let's start with a reminder of what deduplication is. Let's say that we have a storage system with 4 files in it. Each file contains 2 chunks. Some of the chunks appear in several files. For example, the green chunk appears in file 1, 2, and 3. After deduplication, each chunk is now stored just once. You can see here the green chunk stored only one time. Each chunk has a unique fingerprint representing it. And so each file is now represented by a file recipe holding the list of fingerprints of that file. So this deduplication is everywhere today. And so we need to rethink storage functions to suit deduplication. Specifically, we'll focus on the search for a byte string function, which is useful for finding a particular term in a document or for machine learning preprocessing. And we need to keep in mind that we're using offline data, so there's no index for that. So how would a Naïve Search look in a traditional storage system? For looking for a keyword in a traditional storage system, we would simply scan each file's chunk in order. We would go file by file, chunk by chunk, and search for the keyword in each chunk. Here we got 8 chunk reads. When we try to apply this Naïve Search on a deduplicated storage system, we again do the same thing. We simply scan chunk by chunk of every file, but we have several disadvantages. First of all, as you can see, the green chunk has been processed several times, which is not necessary and wastes time and the computation. Then we continue with our scan and pay attention to the rectangle. It goes back and forth, which means that we have a lot of random access, which is very expensive. Last, we need to keep in mind that the chunks are stored in containers, meaning every time we are trying to fetch a chunk, we want to fetch a chunk, we have to fetch the whole container, meaning that entire containers might be fetched several times, which is very expensive and not necessary again. So we thought of the DedupSearch. We developed a better algorithm that is deduplication-aware to search for a keyword. This DedupSearch has 2 phases. First, the physical phase. The physical phase focuses on the physical layer of the chunks stored in the system, and it scans chunk by chunk. For each chunk, we're looking for the keyword in it. We're looking for the keyword matches. And the matches we find, we keep in an intermediate result index. For each chunk, we have an object in the intermediate results according to its fingerprint. Pay attention that we got here only 4 chunk reads compared to the 8 that we had in the Naïve Search. Then we have the logical phase. This is our second phase, where we focus on the logical layer, the file layer, and we read the file recipes. And we're going fingerprint by fingerprint. We're looking now only in the intermediate results. We do not read the chunks. And for each fingerprint, we check what matches we've found in the physical phase, and that's how we collect all the matches. Okay, and our wish is that all the intermediate results would go in memory. So the logical phase would process very fast and won't be expensive. So what challenges did we have here? Let's say that we're looking for the keyword dedup. It is in the middle of a chunk, just to find DEDUP in a chunk. But what happens if a keyword is split between 2 adjacent chunks? So it might be split like that between 2 adjacent chunks, or like that, like one chunk can have at the end of it as a prefix of the keyword, a DED, and the next chunk has a suffix of the keyword like UP. and it may be split in every location. Thus, we have to search also for prefixes and suffixes in our physical phase and keep it in the intermediate results. We have to remember that we saw a DED at the end of a chunk, a prefix that might be later completed into a full match. For that, we're using the ahorasic search algorithm with a bit of modifications. From here, we have another problem raising up of tiny results. Let's say that we were looking for the keyword taste. Then we have to remember to keep intermediate results of every time we see a T at an end of a chunk or an E at the beginning of a chunk. And in the English, in a common English text, every fifth letter is an E or a T, meaning that we're going to have a lot of intermediate results, and it might not go in memory. So back to our algorithm, to the physical phase. Let's go deeply into our phases. So the physical phase focuses on the physical layer. We're going to scan each chunk and keep intermediate results for it. Let's start with the first chunk. So we're looking for the keywords dedup, and we found an exact match here. That's why we are having exact equal 1 for the first fingerprint. We continue in our scan. In the green chunk, we have a suffix of length 1, a P at the beginning. Then we have a suffix of length 2, a UP at the beginning. And in the yellow one, we have a prefix of length 3, a DED at the end of the chunk. So that's all the intermediate results we have here. But our problem with tiny results, how are we going to handle it? For example, here, the green chunk has only a P at the beginning. It's not a rare case to have a chunk with a P at the beginning. So our idea was to split that kind of results to another index. And that index, the tiny result index, would be saved on disk. So for here, fingerprint 2, that has only a tiny suffix, holds a smaller object, saying it has that fingerprint 2 has a tiny suffix. That's how our database looks after the physical phase. Let's continue to the logical phase. So the logical phase now got all its results from the physical phase, and we'll focus on the logical layer, on the file recipes. So we read all the file recipes, and we'll go fingerprint by fingerprint. First, we check the fingerprint 1. We're not reading the chunk, but we go to the index in the memory and see what we found for fingerprint 1. We can see here that we have an exact match in this fingerprint according to our database. And so we output a match in file 1. Then we continue in our scan, and we're checking for each fingerprint the result, the intermediate result in our index. And then we get to file 4. In file 4, we can see in our first chunk, there's a prefix of length 3. Then we continue, and we see in the next chunk a suffix of length 2. So we got here a DED and then a UP, meaning we have a full match that was splitted between adjacent chunks. And we found it, so we output another match in file 4. These are all our matches in this example, but you might have noticed that we didn't access the disk at all. We didn't use the tiny result index. So when would we use that? If we had another chunk with an almost complete match, with a DEDU, meaning only a P is missing for us, only a tiny result is missing. So that's the case when we will go to search for the green chunk in the tiny result, whether or not it has a tiny suffix. So that's for our algorithm. And let's see our experiments. So I'm going to focus here on two data sets, 41 backups of the English Wikipedia and 408 Linux versions. Pay attention that Wikipedia is a much bigger data set, while Linux has much more deduplication. You are more than welcome to check our paper for many other experiments and data sets. So let's start with the main comparison of Naïve Search versus DedupSearch. So on top, we have Wikipedia. On bottom, Linux. On our left-hand side, we have the time comparison, where lower is better. And on the right side, we have the amount of data read, where, again, lower is better. So we can see that DedupSearch outperforms the Naïve Search. It is 8 times faster and almost 99% less data read, which is amazing. Then let's compare. Let's check out the database size of DedupSearch. So again, we have here Wikipedia and Linux. In black, we have the tiny result index, which is on-disk database. And in white, we have the chunk result index, which is the in-memory database. We can see here that most of the intermediate results are tiny. The black column is much higher than the white one, which means that most of our database is stored on disk. But this is great, but we need to make sure that most of our accesses are to memory and not to the disk. For that, we have this table. We compare here the number of tiny accesses or disk accesses of Linux and Wikipedia compared to the number of results we found in these data sets. So we can see here that, for example, in Linux, we have 120K results, while about 200 disk accesses. So we understand here that most of our database is stored on disk, while most of our accesses is to the memory. So we've done here a great job of separating the database. So to conclude, we saw here that deduplication-aware keyword search is much more efficient than traditional keyword search. So this is our main conclusion of our work. And we had some challenges. We had keywords that might be split between adjacent chunks, and lots of partial results coming out of this. And our results and experiments show that we have up to 10 times, up to 10 times faster algorithm, and that we're having up to 99.9 less data read. And all of that with a very compact database and minimum disk accesses. So thank you very much. And you're more than welcome to check our GitHub and ask a lot of questions. Thank you.